Good morning, good afternoon, and good evening. Welcome to this series of webcasts on the DIDCOMM Superstack. This first video provides an overview of how to create highly scalable DIDCOMM agents using Microsoft.NET, the Trinity graph engine, and the Trinsic Okapi libraries. My name is Michael Herman. I'm a self-sovereign blockchain architect and developer, and I live on a cattle ranch in southern Alberta, and those are a few of my cows. The singular goal of this overall project, the Trusted Digital Web, is to make decentralized agent design and development easier for C# and .NET developers. And there's three core tenets to that. One is model-based automatic code generation of the agents themselves, of the verifiable credentials, the structure and schema for those. To facilitate that, we use the structured credential model, which is a superset of the standard verifiable credential data model. And to actually implement both the decentralized agents as well as transport the structured credentials that we create, we're using the Trinsic DID and DIDCOMM libraries. So the agenda will talk a little bit more about the details of the Superstack. We'll go into what I call the Secure Verifiable Credential Transport Protocol, and more in particular the fact that it's enabled from the start, enabled from the get-go to use verifiable capability authorizations. For those that aren't familiar with previous webcasts of mine about the structured credential model, we'll talk about that briefly. And then I'll give you an overview of the demos. The demos themselves are not part of this talk, but they'll follow as part of the webcast series. So the DIDCOMM Superstack is an application framework for creating verifiable capability authorization-enabled, highly scalable, decentralized agents using .NET and DIDCOMM. And in particular, we feature use of the Verifiable Credential Transport Protocol. So there's three basic requirements, and these correspond to the three layers of the stack. So at the bottom of this table, there's the development and execution platform. We're using Microsoft.NET for that. There's the decentralized agent modeling and code generation. We're using the Microsoft Trinity graph engine for the modeling of the agents, the modeling of the credentials, the automatic code generation of all of those components. Internal to the implementation of the decentralized agents is the need for DID key generation, DIDCOMM messaging and credential signing capabilities, and those are provided by the Trinsic Okapi library. The Microsoft Trinity Graph Engine uses something called the Trinity Specification Language, TSL, which is heavily used in the DIDCOMM Superstack. It's used for defining the agents, defining the protocols that the agents use, and the structure of all the messages, including the structure of all the structured credentials that form the payload of those messages. There is an automatic code generator that reads the TSL and produces complete C# projects. Again, objects messages, message handlers, complete HTTP-based decentralized agents, where you just have to fill in some of the implementation details. A nice thing about the Trinity Graph Engine runtime is it supports automatic JSON serialization and deserialization of any structure that's defined in TSL. It's very fast, and part of that, the reason why it's highly performant is it uses a highly optimized in-memory object graph database. So everything you create is initially created in memory. It's serialized and persisted in memory, and then optionally you can persist that to the file system. It has a highly performant and scalable cluster deployment model so that you can have multiple instances of a Trinity server, which is the underlying implementation of a decentralized agent, on a single machine, or you can have those agents deployed in a cluster across multiple machines, and then you can have multiple distinct clusters. In general, you'll find that using Trinity and using TSL supported by the automatic code generation makes things simple, easy, and very efficient to use. The Trinsic APIs or libraries support these basic capabilities: the ability to create keys, decentralized identifiers using the DID::key DID method space, the ability to create DIDCOMM compatible messages, so the ability to pack and unpack messages, the ability to crypt and decrypt those messages, the ability to sign and verify those messages. The third library is the Oberon library, and this is where we create keys for creating digital cryptographic proofs. So we create the keys, we can create an object called a token to support the signing of our structured credentials, and then we can use verify to verify the proof. Lastly, we're using Microsoft.NET as the build and execution platform. The Microsoft Trinity Graph Engine is tightly integrated with the Visual Studio environment to support the automatic code generation, the automatic compilation, the automatic type checking. One thing that should be mentioned somewhere is that a key advantage of the DIDCOMM Superstack is that it's got strong data typing, explicit data typing throughout, so you're no longer just dealing with creating arbitrary strings of JSON. Everything is strongly typed. The JSON serialization, deserialization works. The strong typing forms a canonical representation for serialization and deserialization, and so on. I happen to use Visual Studio Code really as my GitHub client for checking in and checking out code to GitHub. That's just my approach. We leverage a lot of the features in the new C# language. I won't go into any of those details, but when you use that within Visual Studio to do coding within Visual Studio 2022, there's a lot. The IntelliSense is extremely strong in the sense that it's suggesting entire statements as soon as you start typing with variable substitution, and you just literally have to tab through. You get to create a lot of code more quickly, and the code is more correct. And of course, it runs on top of the Microsoft Common Language Runtime, so it's capable of running under any platform, whether it's iOS, Windows, Linux, etc. On top of the DIDCOMM Superstack, we're going to show an example of implementing a DIDCOMM protocol, and this specific protocol is called the Secure Verifiable Credential Transport Protocol, and it's secure because there's a handshake involved where the destination, the subject that you're trying to send a credential to, you first ask them to accept a VCA, a Verifiable Capability Authorization. It's for that particular structured credential. And it's only when they acknowledge, confirm, and accept that Verifiable Capability Authorization that you actually send them the structured credential. So that's the secure aspect of the VCTPS protocol. So the principles that were used in designing and architecting and designing the VCTPS DIDCOMM protocol. The first one I call the self-sovereign principle. That the ability to receive a credential from me, you first have to acknowledge and agree to a verifiable capability authorization that I'll present to you. And we'll see that in a flow diagram on the next slide or two. Reinforcing that self-sovereign principle is the VCA first principle. So VCAs, first of all, are full-fledged structured credentials. Every data structure, every entity is represented as a structured credential. And all VCs are created with a VCA stored in the label component of the structured credential. It's stored as a base 64 encoded property. The VCA can be specific to a requesting party, or it can be generic. Generic implying it's available to anyone, but it's subject to the rights that are specified in the VCA. A VCA has a TTL, time to live after which expires, and access to the referenced VCA is no longer available under that VCA. And the VCA that's attached to a structured credential, this is the VCA that's presented in the notify message that we'll see on the next slide. On what we call the master credential, the master VCA credential, because it's a structured credential, that VCA should have a master VCA. That aspect of the design is not implemented in version 1. When the receiver of VCA confirms and accepts that VCA so that they can receive a copy of the structured credential, they send a VCA acknowledgement back to the originator. And of course, that's represented as structured credentials. And the claims component of that VCA acknowledgement credential, they contain the VCA that was received plus the acknowledgements and acceptance confirmation properties. So the point here is that sometimes VCAs appear in the claim. That's only during the acknowledgement. And every VC is subject to a VCA, and that appears in the label of the structured credential. So here's the definition of the 4 message types in the VCTPS DIDCOMM protocol. Notify, the semantics there are, I have a payload for you, a structured credential. Here's a VCA which includes the structured credential identifier to which you acknowledge and agree to. Send me a pull message containing a VCA acknowledgement confirming your agreement with VCA, and I'll push the payload to you. The pull message says, here's my VCA acknowledgement confirming that I agree to the VCA, and it includes the credential payload identifier. Push me a copy of the corresponding payload, the corresponding credential. So then the originator pushes the credential that was requested, and this is where it contains a copy of the VCA encoded in the payload metadata. So that we have traceability, we have tracking, that when you are the recipient of a VCA, of a VC, it has the embedded VCA within that VC. And those three form the core messages in the VCTPS protocol. There's a fourth message in which the other party, the receiving party, can poll. And basically they ask, do you have anything for me? And if you do, then you send a notify message with a VCA, including the payload identifier. You know, Bob may send out a poll message to Alice and Charlie. Do you have anything for me? And if Alice or Charlie or both of them have a VC to send, then they initiate the notify poll push message flow that we've discussed previously. So here's a visual diagram. So Alice has a VC. Perhaps it's a request for quotation. So she wants to send it out to 3 suppliers, Bob, Carol, and Dave. So she sends that VCA. In that VCA, it has the VC for the request for quotation. Bob or all 3 of them might reply and said, yes, I agree to the VCA, to the Verifiable Capability Authorization. Send me the credential. And then Alice then pushes the VC. And she pushes the VC that has the embedded VCA in it to Bob. So instead of Alice just simply sending the VC to Bob, we have a 3-step process to provide secure access, secure rights-based or capability-based access to the VC. Then there's that 4th message called poll. And this is where Bob sends a message to Alice, Carol, and Dave saying, hey, do you have anything for me? If you do, start the sequence over again. I've tried to map the VCTPS DIDCOMM protocol to the OSI model, and you see that here on the right. So the green represents the technology infrastructure domain of the architectural reference model. The blue represents the application layer, and the top yellow layer represents the business domain. And so if we look on the far right-hand side, the top of our technology infrastructure domain is, you know, the REST HTTP endpoints that our DIDCOMM agent supports. And it's on top of that REST HTTP protocol that we support DIDCOMM messaging. The VCTPS protocol represents specific types of messages that are enabled on top of DIDCOMM. And then finally, once a recipient, for example, Bob, receives a verifiable credential after acknowledging the VCA, he needs to do something with it. And so what we do is we drop into a business layer BPMN defined application workflows for processing that VC. So we have very distinct layers with very distinct responsibilities. This was emphasized once the steps for the VCTPS protocol were defined, those 4 steps of notify, pull, and push, because there is a flow there that needs to be managed, but it's a flow within a particular layer of the model. And it's only once that flow defined by the VCTPS DIDCOMM protocol is complete for a particular series of interactions that you then drop into the higher level and process the received VC using a business workflow. This is a quick explanation of what a structured credential looks like. And a structured credential is a superset of a verifiable credential. So, here's a simple credential, bound credential, for something from a hypothetical DID method space called colors. And in the structured credential model, we talk about a sealed envelope. So a sealed envelope is the entire JSON structure, including the proof at the bottom. That proof represents the seal. By checking the proof, that's how we determine whether the rest of the content of the envelope has been altered or not. Inside the envelope, we have the credential content. The primary component of the credential content is the credential subject, which is the ID and the claims, the bottom half of that credential content rectangle. And of course, the way the description for those claims is defined by the context. So the context and the credential subject comprise the credential content. And here you see that visualized here. Here's the claims that are part of the credential content, and then outside the credential content, on the face of the envelope, if you will, is a packing label. And this contains primarily the type information, identifying it as a verifiable credential, identifying what type of credential it is, etc. If we take the packing label and the credential content, we add to that an envelope seal, aka a verifiable credential proof. And we attach that proof to the outside of the envelope, to the outside of the contents of the packing label and the credential content. And that's what gives us a sealed envelope. So here's an example of a credential envelope, a sealed credential envelope. So there's the envelope itself, which contains the credential content. We can't see that in this picture. We have a packing label that we then attach to the envelope. We have a seal that we attach once we close the flap on the envelope, which has the credential content inside. And that proof, of course, is calculated based on the content of the envelope content of the label. And then on the outside of the envelope, the top outer level of the credential JSON, we have the envelope identifier. So just to overview the demos. The demos are based on a scenario where ABC Grocery, on the left-hand side of this picture, wants to order some cabbages. And they want to send out a purchase requisition, a purchase order, to be specific, to 3 different suppliers: Mary's Market Garden, David's Cabbages, and Paul's Produce. The schema for those purchase orders and all the other documents business documents we have here is based on UBL 2.2, the Universal Business Language version 2.2 schemas. And so once that purchase order is sent out, a sales order or order confirmation is returned. We go through a series of interactions between the supplier and the freight forwarder to have a waybill produced. And we have a series of transportation status events or credentials that are returned until we ultimately receive a delivery confirmation. And once we receive confirmation of that delivery, whoever the supplier is will send an invoice for the final amount. So think of these as a series of layered prototypes, a sequence of prototypes starting with the simplest scenario to the more complex. So prototype 1, the goals there are simply to create a DIDCOMM agent that accepts encrypted DIDCOMM messages. We model the message structures, the DIDCOMM protocols, and the server implementation entirely using the Trinity specification language. And we use automatic code generation to build the entire server. There's maybe 10 lines of code we have to add to the finished C# project. And then another few lines to actually send an HTTP message to the server we've created. And we'll see a worked example when we look at the prototype 1 webcast. Prototype 2 builds on prototype 1. It takes the Trinity libraries and it starts by creating an encrypted DIDCOMM message. And we have a dummy verifiable capability authorization that we're going to send as part of a notify message in the VCTPS protocol. But more simply stated, we send an encrypted DIDCOMM messages. So we have to create a few subjects, and we use the DIDCOMM, the DIDKey libraries for those. And then we use the DIDCOMM capabilities to encrypt and decrypt the message on sending and receiving respectively. So the goal is simple, just simply to send a notify message to the DIDCOMM agent created in prototype 1. We're not implementing the entire VCTPS protocol. We're just simply sending a notify message as an example. And then we want the DIDCOMM the DIDCOMM agent to receive, accept, and decrypt that notify message. Just for completeness in terms of the discussion of the Trinity graph engine component of the platform, we'll show how to save that message into Trinity local storage. Prototype 3 builds on prototype 2. We do some refactoring there to move some of the HTTP processing and queuing and processing of the DIDCOMM messages into some separate classes. And we're going to show a fairly sophisticated flow where a DIDCOMM message is going to be addressed to multiple subjects. And although we only have one physical instance of the DIDCOMM agent being processed, we set up queues for each of the destination subjects, each of the targets. So in effect, we're simulating multiple agents asynchronously receiving DIDCOMM messages, decrypting them, and then queuing them for processing. Prototype 4 builds on prototype 3 simply by improving the multi-threaded asynchronous processing of the incoming messages. Because of the way that the prototype 3 posted the HTTP messages, being sequential, the whole processing within prototype 3, although it was designed to support parallel processing of the incoming messages, received incoming HTTP messages sequentially, and so prototype 4 is simply a design improvement on prototype 3 with no significant increase in functionality. Prototype 5, we model the verifiable capability authorization, verifiable capability authorization acknowledgement using TSL. And we place the dummy VCA used in prototypes 2 and 3 and 4 for that matter with the VCTPS DIDCOMM protocol model created in this version of the prototypes. We create some helper methods for working with VCAs, VCA acknowledgements, and we introduce for the first time some, the higher level universal business language structured credentials for invoices, parties, and items. And we go through the process of initializing 3 items for 3 different products, cabbages, cauliflower, cucumbers, or something. And then the 12 people that were involved in that flow diagram that we talked about earlier. So prototype 5 is really just an intermediate step to showing the complete VCTPS flow. Prototype 6 actually was a failure. The goal there was to create a complete UBL compliant invoice verifiable credential with all the possible properties. And it turns out that when you get deeply into the UBL specification, in this case we automated the processing of the XSD definitions for invoices, waybills, etc., and all the subtypes. And it turns out that the subtypes are some 12 layers deep, and it produced enormous structured credential objects. So, and as a result, some huge automatically generated C# classes. So we sort of abandoned prototype 6, but it's there because there was a lot of code created for it, and it kind of set the stage for 7. So in 7, we simplified the schemas for purchase orders, sales orders, delivery receipts, and invoices. And this is the first prototype to show all the layers in that OSI diagram where we're creating UBL compliant structured credentials with proofs using the Oberon library. We're sending those to multiple parties following the VCTPS DID protocol, the notify, the pull, and the push messages specifically. Those are being transmitted using DIDCOMM and being encrypted and decrypted using the Transic libraries. We use Transic DID keys for all the identities for all the subjects. And we use the same automated, automatically generated definitions, C# code for the decentralized agent. So this is where everything comes together. Resources, again, just kind of organized around the 3 layers in the DIDCOMM superstack. So for Transic, DID and DIDCOMM libraries, there's the GitHub repository, and the best place to look for examples, coding examples, for C# developers. Again, these libraries are available to support more than half a dozen languages, I believe, language environments. But for .NET, you can go to the .NET/test/OKAPI tests folder on GitHub, and you'll see examples of creating DID keys, of doing DIDCOMM message creation using encryption and decryption, and you'll see the Oberon libraries for creating proofs. The Trinity Graph Engine, also an open source project, is available on GitHub. The documentation can be found at the graphengine.io website. Fairly complete, and there's some great examples described in the documentation, and the code is on GitHub, and you can see the link for the examples. The DIDCOMM Superstack, there isn't a lot of documentation other than this deck and the examples themselves. And most of this, all the code can be found on GitHub in the VCTPS Prototypes project. If you'd like to learn more about the structured credential model, because it's greatly simplified the modeling and greatly simplified the coding of verifiable credentials, particularly using a strongly data typed environment like we're using here. So hope you've enjoyed what you've seen so far. If you have any questions, you can send me an email message at mwherman@parallelspace.net. And I hope you've enjoyed this talk.